So welcome everyone for the third and last of the Paul Bernays lectures 2023. And then Professor Buzzard will tell us all about the liquid tensor experiment.
So, right, thank you very much for coming, as ever. My lectures seem to have a half-life of about 50%, so congratulations for surviving this long. And also, if you came to the others, you might have become convinced that I'm some kind of chancer who doesn't know anything about anything and is just waffling on about AI. But I am actually going to I'm going to prove to you that I am actually a mathematician now by doing some mathematics. I still do identify as a mathematician, I should say. So this is a talk about some work that a big team of people did, like 10 plus people did in the last couple of years. And it was involving, I somehow left the last lecture saying we had complicated proofs about simple things, and we had simple proofs about complicated things. And then the question was, could we have a complicated proof about a complicated thing? So let me spend the first 40 minutes explaining a complicated thing. Before I start, let me say that really, I'm part of a big community called the Lean community, and I'm not representative of that community. I'm just, we're just all one big team, really, and if you want to attribute, if you want to really attribute sort of credit to this work, a lot of the work was done by these two people here, Johan Commelin and Adam Topaz. So I'm going to talk to you about a complicated theorem and the fact that we managed to teach it to a computer and my conclusions. Right, maths. And then after maths, lean, and then after that, a page of waffle. So maths. So homological algebra, it had its origins in maybe the early 1900s, where people trying to understand algebraic topology, sort of simplicial or singular homology. But after a while, it became a general tool that you could develop just completely abstractly. And then people found applications in other places, like sort of computer. There was a homological algebra revolution in commutative algebra. Basically, the introduction of homological methods was a very key thing. And by the 1960s, Grothendieck also used it as a very important component in his treatment of algebraic geometry. And what is homological algebra? We could summarize it by saying the key idea is this idea of a complex of objects. So what's going on here? All these CNs and Cn plus 1, these are all, say, abelian groups, or real vector spaces or something. And there's maps. So the n is running over like the naturals or the integers. And there's maps from Cn to Cn plus 1, or sometimes maps from Cn to Cn minus 1, depending on if you're doing homology or cohomology. And all the maps are called D. Sometimes, if people are being careful, they might put Dn at the beginning, and then like 2 slides later, they just call it D. So all the maps are called D, and the axiom is that D squared is 0. So that's somehow the key gadget, this idea of a complex. And these complexes became a key tool for studying homology and cohomology as we developed a more abstract understanding of homology and cohomology theories. So initially, these CNs were abelian groups. They were sort of, things like functions from an n simplex, continuous functions from an n simplex into a topological space, or the free abelian group generated by those things. So they were abelian groups, or they were modules for a fixed ring R. But after a while, when more advanced techniques appeared, people like Grothendieck wanted them to be more abstract objects. So instead of having to set up the theory for abelian groups and then set up the theory again for modules and then set up the theory again for sheaves of modules or whatever, the idea is we should try and figure out what exactly we're using. And so Grothendieck, was it Grothendieck? I should have checked this. Certainly I learned about abelian categories from a paper of Grothendieck, but the idea crystallized of the concept of an abelian category, which is which is sort of a pretty general setting where the idea of a complex works. So what's an abelian category? Well, first I'll tell you what an additive category is. An additive category, so a category is just objects and morphisms, and in an additive category, the collection of morphisms from A to B is an abelian group. And that's the sort of the key new thing that separates additive categories from categories. And certain natural things are group homomorphisms. An abelian category is an additive category where we demand quite a lot more. We demand that our objects are very well behaved. And you could sort of summarize it by saying sort of kernels and co-kernels exist and have the properties you would expect of them. So there's a vague idea about what's an abelian. I mean, the definitions don't matter. They mattered to Lean, but they don't really matter in this context. Because I just want to give you some kind of feeling as to what's going on. And so the idea is that we can talk about complexes of objects in an abelian category. And I didn't tell you I didn't tell you the precise definition of an abelian category, but let me tell you some key thing is that if you have a morphism in an abelian category and it has no kernel and no co-kernel, then it had better be an isomorphism. So kernels and the kernel and a co-kernel, I mean, more precise, kernel is some kind of limit in this category, and a co-kernel is a co-limit, but just to be very concrete, imagine if A and B are abelian groups, then you know what the kernel of a map from A to B looks like. It's just the things get sent to zero. And the co-kernel, you can just think of it as the target quotiented out by the image. So in the category of abelian groups, it's certainly true that if you've got a map with no kernel and no co-kernel, then it's injective and surjective, and so it's bijective, and a bijective map between abelian groups is an isomorphism. And so that's sort of morally what the axioms for an abelian category are telling you. A bijective morphism has an inverse. But of course, for category theory, objects don't have elements, so that doesn't make sense. Like the concept of bijective doesn't make sense, but you can get around it using category theoretic language. So this is the idea. So what kind of categories do you know where bijective morphisms have inverses? And sort of algebraic categories, like the category of sets or groups or rings or R modules for a fixed ring R, all of those categories have that property. A bijective morphism has an inverse. But the category of topological spaces, this is not true. You can have a continuous bijection between topological spaces, X and Y, and continuity. So it's a continuous bijection from X to Y, so we may as well imagine that X and Y are the same set, and with two topologies, and the fact that it's continuous just means that the Y topology is a subset of the X topology. Everything that's open for the Y topology is also open for the X topology. So it's just an inclusion, right? X has got at least as many open sets as Y, but it might not have exactly the same number of open sets. And it's easy to write down examples of continuous bijections that don't have a continuous inverse. So topological spaces aren't going to be an abelian category, but they're not even an additive category. But if you instead use topological abelian groups, that is an additive category. Given two topological abelian groups, the maps between them naturally have an abelian group structure. But this kernel and co-kernel being zero implies an isomorphism. Is not going to be true. So topological abelian groups are not an abelian category, and there's a completely, just to check, there's a completely explicit example. Let B be, I don't know, like the real numbers with its usual topology, and let A be the real numbers with every set is open, because there you go. I mean, I've said this twice already, so. There's an explicit example, and another explicit example of why topological abelian groups aren't an abelian category is you can get maps with dense image, and these are a bit terrifying. So, for example, if V and W are Banach spaces, it's quite common that you can have a map from V to W with dense image, and then the co-kernel is supposed to be a well-behaved object, but the co-kernel of a map with dense image is going to be sort of a non-Hausdorff horrible object. So the category of topological abelian groups is sort of slightly terrifying. But the thing is, when you're just doing algebraic geometry, you tend not to see topological abelian groups. You're looking at spaces of functions, but they might be, these are functions, polynomial functions defined over an arbitrary field K that you want to vary maybe. And and K probably doesn't have a topology in algebraic geometry. But when you're doing differential geometry, you might be working over the real or the complex numbers, and now suddenly your base object has got a topology, and your spaces of functions have also got a very natural topology as well. And you start running into these issues. So this is somehow the problem. If you want to do, if you're interested in real or complex manifolds, or even if you're interested in, p-adic manifolds, which some people are, or p-adic rigid spaces, then you still want to use the amazing tool of cohomology. You want to do things like de Rham cohomology, but you don't have access to all this sort of fancy technical machinery like the theory of derived functors that will just apply instantly. So this is somehow the argument is that this is a problem because it would be nice to develop some differential geometry or some analytic geometry using these amazing tools that we have, these homological algebra tools, but you can't use them because you don't have an abelian category. And I should say that people have tried to solve this in the past. Well, that's a spoiler, I should go back. People have tried to solve this in the past by, axiomatizing. They're not quite an abelian category, but it's not too far from being an abelian category, and maybe we can get some of the theory working anyway. But the wild idea of Clausen and Scholze is maybe the whole concept of topology is wrong anyway. I mean, is not an appropriate thing to be using in this context. So let's get rid of topological abelian groups and try to do something else instead. So we need to come up with a different idea instead of topological spaces. And here's the idea. The idea is that it's not true that every topological space is somehow determined by maps from compact Hausdorff spaces into it, but a very large class of topological spaces are, including the kind of topological spaces that geometers are interested in. Maybe not the kind of topological spaces that topologists are interested in. If you're just finding weird counterexamples, then you might not be so keen on this idea. But if you want to do differential geometry or something like that, or study Banach spaces, then the idea is that maybe we're not losing too much information by replacing X with all the maps from all compact Hausdorff spaces into X. So curly letters denote categories, so curly CH is the category of compact Hausdorff topological spaces, and now the idea is if X is any topological space, then instead of X we're going to consider a functor called Fx, and that's the functor, the contravariant functor from compact Hausdorff spaces to sets, sending S to the set of continuous maps from S to X. So the idea is, instead of X, we're going to try and work with Fx instead. And so there we go. Now we've got so now Fx is a functor, but the map sending X to Fx is also a functor. This is now a functor from the category of all topological spaces to a category of functors. And you can see that we must have lost some kind of information because, for example, this functor isn't fully faithful in general. So you could imagine there might be two topological spaces, X and Y, that were somehow maybe not isomorphic, but the corresponding functors might be isomorphic because the spaces are so sort of wild. They're not isomorphic because they're locally incredibly large and non-compact somehow. But just compact Hausdorff spaces can't pick up on that. So these functors Fx, we've lost some information. In particular, if our topological space X turned out to be very pathological, then we might have lost some information. But if our topological space is compactly generated, which basically means the definition of compactly generated is we haven't lost any information, then this functor is fully faithful. And so I won't tell you what compactly generated is either, but let me just give you some examples of compactly generated spaces. So anything that's sort of finite dimensional, anything that's sort of locally compact in Hausdorff, right? Any manifold or any CW complex. And I think any first countable space is compactly generated. In particular, any metrizable space is compactly generated. So any Banach spaces as well. So the kind of X for which we're losing information are really quite weird things that some people might well study, but if you're interested in differential geometry, then you might not be so interested in these weird spaces that we're losing track of. Right. So here's a key definition then. So normally these are called condensed sets in the literature, but I'm quite anti the whole idea of a set because I'm sort of used to doing mathematics in type theory now. So you all see a collection of stuff and you call it a set, whereas I now see a collection of stuff and I call it a type. But here, we don't call them topological sets or topological type. We call them topological spaces. A space is supposed to indicate that there's some kind of geometry going on or some kind of topology. And this whole point about condensed is supposed to be some replacement for topology. So let me call it a condensed space. But in the literature, it's called a condensed set. So a condensed space is one of these functors. It's a functor that eats a contravariant functor. It eats compact Hausdorff space. It eats a compact Hausdorff space and it spits out a set. And then these two axioms, axioms 1 and 2, just say that f commutes with certain finite. F sends a finite coproduct to a finite product, and f sends a co-equalizer to an equalizer or something. It says f commutes with certain very simple constructions in mathematics. And why have we put these axioms in? Well, it turns out that if the example we've seen, this map, given a topological space, then this map sending S to Homs from S to X, satisfies these two axioms. So the first one is relatively straightforward. How do you give a map from a disjoint union of two sets to X? Well, you just give two maps, right? One from the first set and one to the second set. So the first axiom is clear. The second axiom is slightly trickier. You need to use the fact that a surjection of compact Hausdorff spaces is a quotient map. In compact Hausdorff spaces, you don't have this phenomenon that you can get bijections which aren't isomorphisms. Very well-behaved category, compact Hausdorff spaces. So this isn't an immediate diagram chase. You have to think. If you get bored in the lecture, you could try proving two. So, those of you that know what's going on, strictly speaking, I didn't actually tell you the definition of a condensed set, because if you insist on doing mathematics in using set theory, which, as I say, is the tradition, and if you insist on sticking to this, then it turns out there's size issues. You sometimes might want to take some limit over something which isn't a set. And I'm not going to go into those size issues at all, and I thought I may as well mention Bernays, given that these are the Bernays lectures, and one of his contributions to mathematics was to observe that there's no reason that you need to sort of stick to sets, and then these things which are bigger than sets, you can't really talk about them properly. This NBG, Neumann-Bernays-Gödel model of mathematics, he allows classes to be first-class citizens. And the same sort of thing goes on in Leans-dependent type theory. Leans type theory, everything has to have a type. So, the reals has to have a type, so it's a thing called type. But then type has to have a type as well, so it's a thing called type 1. And type 1 has to have a type, and that's called type 2. And so there's this infinite collection of universes. And if you just use these universes, then all the set theoretic issues, they don't go away, but they get moved to somewhere else. So they've been moved, in particular, they've been moved out of the talk. So there you go. So I don't need to worry about set theoretic issues at all, because I'm not doing set theory. I'm doing type theory. And then I guess the other remark I want to make is that compact Hausdorff spaces are sort of nice things that we kind of understand, but profinite topological spaces are slightly scarier. So a profinite topological space is just a projective limit of a finite discrete topological space. In particular, it's a closed subset of a product of finite topological spaces. So they're going to be compact in Hausdorff, because arbitrary product of finite topological space is compact, and arbitrary product of compact is compact, and closed subset of compact is compact. So profinite topological spaces are examples of compact Hausdorff spaces. And if you're more on the algebra side of things, you've seen things like the p-adic integers. These are examples of a profinite topological space. But if you're a differential geometer, then you might be slightly scared of these objects. So they feel very zero-dimensional, but topology doesn't care about the concept of dimension. Here's a great example of a continuous map, which I learned from this Scholze paper. So what do we start with? In the left-hand side here, we have a profinite set. It's just a countably infinite product of finite sets, and the finite sets are just digits, 0 up to 9. So so an element of the left-hand side is an infinite string of digits, and you can put 0 point in front of it, and now you've got a decimal, now you've got a real number. A real number between 0 and 1. You've even got 1, right? You've got 0.9 recurring. And so this is a surjection from this 0-dimensional thing to this 1-dimensional thing. And it's but it's not a bijection at all, right? Because like 0.19 recurring equals 0.2. So in fact, this is a quotient of this by some really quite complicated equivalence relation, where things that end in 9 are equivalent to things that end in 0. But somehow, in this, like 0.19 recurring and 0.2, those are quite a long way apart in this space here, and they've been identified here. So something quite weird is going on with this map. But basically, this is saying that you thought this is not profinite, right? This is definitely not a limit of finite sets. Profinite sets are totally disconnected. The only connected subspaces are the one-point subspaces, and obviously closed knot one is connected. So there's a weird surjection from a profinite set to a compact Hausdorff set, and in fact this is not just closed knot one is small. It's actually generally true. Every compact Hausdorff space is a quotient of a profinite space, because you take your compact Hausdorff space, you then throw away the topology completely, and then now you've got a discrete space, and then you look at the Stone-Check compactification, which is an incredibly large profinite space. So it turns out that actually when you're defining condensed sets, you don't need to use all compact Hausdorff spaces as test objects. You can use profinite spaces if you like, and you get the same theory. And I want to give you an example of a compact Hausdorff space that will come up again. And this example happens to be profinite as well. And it's the following example. You know it's compact Hausdorff because it's a closed and bounded subspace of the reals. It consists of the reciprocals of the positive integers, and then take the closure. So 1, 1/2, 1/3, 1/4, and then throw in 0 as well. So that's a closed and bounded subset of the reals. So it's compact Hausdorff, but it's also 0-dimensional, so it's not surprising to see that it's also profinite. I say it's not surprising. I was really surprised. I thought that all profinite sets were like finite or uncountable. I was slightly taken aback when I discovered that this countably infinite space was profinite. But it is a profinite space. Okay, so we're going to start with a topological space, and we're going to define this functor fx that sends S to the maps from S to X. And now we want to try and work out how much stuff we've actually lost. And one thing is we can certainly recover X as a set, because if S is just a one-point set, then that's a compact Hausdorff topological space, and the maps from a one-point set into X are just X again. So we haven't recovered the topology on X, but we've recovered the underlying set. If we just had fx, and we had to now reconstruct X, at least we can reconstruct the underlying set. And also, more than that, if we use this funny compact Hausdorff space I was just talking about, we can also recover the concept of what tends to what, which sequences tend to what limits. If we know fx of S, we know all the maps from S into X. And so, in particular, we can work out whether a sequence tends to a limit and which limit it tends to. And so, we might have lost the topology, especially if X is super pathological. But clearly, we've not lost much of the topology. Things like, we can still talk about a limit of a sequence, even if we only have the functor fx and not X. So we're clearly still. It's not unreasonable to think about fx as having some kind of geometry or some kind of topology. Great. So now let me explain what was going on with that definition. The definition was it was a functor and it satisfied two axioms. It commuted with some limits. But in fact, what's really going on is that a contravariant functor. Some people call a contravariant functor on a category a presheaf on that category. And this is because if you have like a topological space, you can make the category of open sets on it, and a presheaf on it is just a contravariant functor from that category. But you can't talk about sheaves on a category unless you give the category some extra structure, and the extra structure is a Grothendieck topology. And a category with a Grothendieck topology is called a site. These compact Hausdorff spaces, they are a site because your topology is a bunch of maps or an open cover if the union is surjective. a map from finitely many compact Hausdorff spaces to a compact Hausdorff space, such that the union of the images is surjective. That's an open cover. And that gives you a site. And then those axioms I wrote down, it just turns out that I've just written down completely concretely the concept of sheaves on this site. So really we're looking at sheaves on the category of compact Hausdorff spaces. And in particular, we're looking at the category of sheaves on a site. And the category of sheaves on a site are really, really nice objects. This is what a Grothendieck topos is, the category of sheaves on a site. That's one definition. And because, Grothendieck topoi are very nicely behaved objects. And in particular, I'm claiming that we fixed this problem that we had with topological abelian groups. So we can define condensed abelian groups. We have to figure out what that is. So there's like three ways of defining it. We could be super abstract and say, oh, it's an abelian group object in the category of condensed spaces. That would work. Alternatively, we could say, well, a condensed space is a sheaf of sets on this site, or a sheaf of types, or a sheaf of whatever your collections of stuff are. But if you instead consider a sheaf of abelian groups, then that should be a condensed abelian group. But there's a totally concrete definition where you just look at that functor from compact Hausdorff spaces to abelian groups, satisfying those two axioms. So there's a condensed abelian group, and it's just the same. Every topological abelian group will give you a condensed abelian groups, and sensible topological abelian groups will be there, and sort of weird topological abelian groups might not be there, and there might be weird condensed abelian groups that aren't topological abelian groups, but sort of the core of both of these definitions, topological abelian groups and condensed abelian groups, there's a whole bunch of stuff that mathematicians are interested in, and we haven't lost too much of that stuff. So this is not difficult. I called it a theorem, but maybe it's more of an observation. It's the kind of thing that you can sort of go away and try and prove yourself. The category of condensed abelian groups is an abelian category. So it's a theorem because it's important, not because it's difficult. The idea is topological abelian groups are not an abelian category, but condensed abelian groups are an abelian category, and they contain 99% of the topological abelian groups that we'll ever care about. And so now let's try and work out how we fix the problem. So there's a continuous bijection from the real numbers with the discrete topology, so like every subset is open, to the real numbers with the usual topology. That's a continuous bijection, and it doesn't have a continuous inverse. And so why doesn't this? But these are reasonable topological spaces, so they're definitely condensed. So why does this not contradict the previous theorem? And the reason is that the category's changed, and so the limits have changed as well. So in the category of topological abelian groups, you can check that the co-kernel of that map is 0. But if you look at the co-kernel in the category of condensed abelian groups, you see a different story. So the co-kernel is going to be some functor, and you can evaluate the functor at lots of places. And so you can evaluate it at a point, and then you just get the usual co-kernel of this bijection, so it's 0. But if you try and evaluate the co-kernel of this funny set S, then f of S is huge, and the reason for that is we've got these two topological spaces up there, but I could think of them as condensed. I can think of them as condensed abelian groups. And so what are the big question is, what are the continuous maps from this funny set S into these two topological spaces? And the point is, for the reals with the usual topology, it's kind of clear. We've got 1 over n goes to xn, which is a real number, and then 0 goes to the limit of the xn. But for the reals with the discrete topology, when does a sequence converge with the discrete topology? Has to be ultimately constant. Has to stop moving. And so f of s for this first thing only has locally constant functions, whereas f of s for the second thing is much bigger. It has all limits of all sequences. And so you can see that the topological spaces look very similar, but the condensed sets, this somehow right-hand condensed set is much bigger in some funny sense. So that's why this example doesn't contradict my claim that this is an abelian category. And in fact, the co-kernel is a great example of a condensed abelian group, which is a completely new kind of object. Right? It's very far from being a topological abelian. If it were a topological abelian group, we could work out what the underlying set was by evaluating a one-point set, and then you get 0. So you can sort of now begin to sort of see the subtleties of this definition. So now I want to talk about completeness, and completeness is not a topological concept, right? The reals and open 0, 1 are homeomorphic, and one is complete and one is not. But you can talk about metric spaces being complete, and there's something called a uniform space that lives between a metric space and a topological space, and you can talk about uniform spaces being complete. And that's the reason why we can talk about a topological abelian group being complete. What you can't do with a topological space is, given two distinct points in that space, you can't compare the bases of neighborhoods at these two distinct points. But if you have a topological abelian group, and you've got two distinct points in this group, then given a neighborhood of one point, you can just use the group law to move it to a neighborhood of the other point. So in particular, even though you don't have a metric, you can still make sense of things like A is about as close to B as C is to D. That sort of idea begins to make sense. And so you can make sense of Cauchy sequences, and so you can talk about topological abelian groups being complete. And so now, what does it mean for a condensed abelian group to be complete? This definition isn't going to fly because we're not doing topology at all, so we need to come up with a completely different definition of what it means for a condensed abelian group to be complete. And this turns out to be a super delicate question. So before I start explaining the answer to the question, let me tell you why I've suddenly started talking about completeness. And the reason is that what we want to be able to do linear algebra, right? We've got this complex of stuff, and I want to look at HOMs between two complexes, or extension groups between two complexes, this sort of thing. We want to start doing linear algebra, and the one thing that, basic linear algebra works fine, but the one thing that doesn't work so good is tensor products. And tensor products are a bit of a nightmare in this sort of situation. So I don't know if you've ever thought about objects like this, but R tensor R, this is a gigantic thing. This is not the kind of thing that you can sort of understand. It's gigantic and pathological. And QP tensor QP. So these abelian groups are huge. They're much, much, much bigger. They surject onto R, but sort of the kernel is incomprehensible. So these tensor products are huge, and if you've done any kind of sort of p-adic geometry or differential geometry, you might well know that what you do is you take the abstract tensor product, and then you complete, right? This is not the kind of thing that you should be thinking about. The idea is you look at these tensor products as like finite linear combinations of tensors, but you want like infinite linear combinations of tensors that are getting smaller and smaller. That's the kind of object you want to talk about, and so you need to sort of take an abstract tensor product and then complete. That's what people tend to do. And then still there's lots of problems, but this is sort of one way of taming tensor products is by completing. And then Grothendieck in his thesis, before he became an algebraic geometer, Grothendieck in his thesis, he thought about tensor products of topological vector spaces, and he found that even with this idea of completion, the theory is very subtle. There's like several different ways of topologizing the tensor product, and then they give you different completions, and it's sort of slightly hairy. But we want tensor products, so we want some kind of, we can do tensor products of condensed abelian groups, and we get large pathological things, and then we want to somehow complete them and make the pathologies go away. So the first attempt to fix this issue that tensor products were sort of wild and incomprehensible was the idea of a solid abelian group. And so in brief, what's the idea here? We've got a condensed abelian group V, and the idea is this condensed abelian group is going to be solid if S is any, well, I'm going to stick to pro-finite. I'm not sure if this is true for compact Hausdorff. This is why I mentioned pro-finite. V is solid if you have an arbitrary pro-finite set and an arbitrary continuous map from this pro-finite set to your condensed abelian group. And the idea is that map should always extend to some slightly bigger space of the space of sort of measures on S. So an element of S gives you a measure on S, gives you like the Dirac measure. But there are more general. This is just, M of S is just, you look at continuous maps from S to the integers, and then you look at the Z dual of that. That would be the space of measures. So this is a space that's typically bigger than S, and the idea is that any contiguous map from S of E should extend to such a map like that. So there's a definition of, I mean, this won't come up, you don't need to memorize this carefully. This is not really going to come up again. This was their first idea of completeness. And so now, so there's just some criterion, and you can prove theorems about that criterion. And one of the things they prove is that solid abelian groups, they're an abelian subcategory. So it's what they prove is really, once you're solid, it's really hard to stop being solid. Did I put that? Yeah. Once you're solid, you stay solid. So, for example, a limit of solid abelian groups is solid. A co-limit of solid abelian groups is solid. Extension of solid, like if A and C are solid, and A to B to C, 0 to A to B to C to 0, then the middle thing is also necessarily solid. So this is a sort of a really robust subcategory, and the idea is that this is supposed to be the V's that don't have any holes in. So there's solid, and there's obviously an inclusion functor, a forgetful functor, from solid abelian groups to condensed abelian groups, and it turns out that functor has an adjoint, and that's solidification. So now so that's completion, right? So given a random condensed abelian group, you can complete it. And so it turns out that there's a perfectly good theory of tensor product of solid abelian groups, and you just do the obvious thing. You take your two condensed abelian, you take your two solid abelian groups, you form the tensor product in the category of condensed abelian groups, which is not too difficult, and then you solidify. You apply this adjoint of this inclusion, and that turns out to be a good theory of tensor products for solid abelian groups. So that's great. So now we've got all the things we need. We can start, dreaming about six-functor formalisms and, revolutionizing geometry and applying fancy algebraic techniques to, in more generality. But there's a big problem, and the big problem is that it works great for p-adic numbers. So p-adic Banach spaces these things are really easy to prove, right? How do you get a p-adic Banach space? You start off with, how would you do it? You would take, I guess I could take the integers, those are solid, and then I could do the p-adic completion of the integers. I get zp, that's solid. And then I could take an arbitrary product of zp's, and that would be solid. And then I invert p, and localization also preserves solid. And so I invert P, and now I've got a p-adic Banach. That's why p-adic Banach spaces are solid. So it's difficult to become unsolid once you're solid. And even, p-adic Frechet spaces are solid, and the integers are solid. Lots of things are solid, but unfortunately, the real numbers are not solid. And when you solidify the real numbers, you get 0. And so if you want to apply this stuff to sort of p-adic geometry, then there you can do it. But in p-adic geometry, we're already quite good at cohomology theories. What really they were targeting was things like the theory of complex manifolds. So the solidification of the reals and the complexes is going to be 0, and so we need a more subtle theory of completion. So in an attempt to rescue the theory, so if you've looked at Scholze's notes from the courses he's been giving in Bonn on this stuff, that's like the first, we've now covered like the first lecture course he's given, the solid stuff. But in an attempt to rescue the theory, because we want the real numbers to be complete in some way, they now define a slightly weaker concept of completion called P liquid. And now P was a prime number on the last slide. P is a real number between 0 and 1 for the rest of this talk, in fact. So P is a real number between 0 and 1, and it's the same kind of definition. So now I'm not going to define what it means for a condensed abelian group to be P liquid. I'm going to stick to, right, because the problem is the reals. So a condensed real vector space is P liquid, and it's the same definition. You've got a map from S to V, and it has to extend to a map from some space of measures to V. But now I've got to say what this space of measures is, and now this is subtle because you really have to, say exactly what the condensed structure is. So I'm not going to go into the details. But this is some completely concrete. This is like countable sums of Dirac measures with coefficients whose the sum of the qth powers is sort of finite. That's the sort of definition it is. And so there's some other definition of completion which is sort of related to but not quite the same as the one we saw before. And the big theorem, and now this is a big theorem, is that P-liquid vector spaces are also a great abelian subcategory. So it's very difficult to cease being p-liquid if you start being p-liquid. And now, this time, the reals work. The reals are the p-liquidification of the reals again. And so this is the thing we want, is now the hope is that we'll be able to use algebraic techniques in geometry. But unfortunately, this theorem's really hard. This theorem is basically the main content of the second Scholze course from Bonn, so analytic.pdf. So assuming that theorem, we can now, they do amazing things assuming this theorem. They define a new category that they call analytic spaces. And normally when you're doing an analytic spaces, you do like complex manifolds, so you're over the complexes, or p-adic manifolds and you're over a p-adic base. But they have some general definition of a category that contains all complex manifolds and all p-adic manifolds and various weird other things as well. That they can define using these techniques. And now they can start proving theorems about analytic spaces and start making deductions in the theory of things like compact complex manifolds. So these are proofs. Some of these proofs are hard because you just have to get your hands dirty and do some analysis, do some Hodge theory or whatever. But all of the analysis can now be removed if you use this fancy liquid vector space stuff. So what remains really, so what I'm going to talk about now is how do we prove this main theorem of liquid vector spaces? So it's a series of reductions, as is often the case. So the first thing we want to do is we've got this funny space of Q measures on S, and I want to so that's liquid. And I want to check that, and if V is a P Banach space is a Banach space, except the norm of lambda V is not the norm of lambda times the norm of V. The norm of lambda V is the norm of lambda to the power of P times the norm of V. So it's some slightly weird, twisted version of a Banach space. But those are liquid as well. Those are p-liquid as well. And we kind of need to check that this is extensions of p-liquid things are supposed to be p-liquid. So the first derived Hom of this should be 0 at least. But the idea is that all the derived Hom should be 0. So this is some derived functor applied to this Hom functor. And this is what we have to prove, is that we've not introduced some weird extra extensions that weren't there before. Yeah. Have I got a Q? Oh, yeah, sorry. Yeah, Q is less than P. Sorry. Yeah, this is correct. You know, you knew that already, right? Yeah. Initially they started to use Q equals P, but then there's some weird thing to do with entropy that doesn't work out. So they use Q less than P. The next thing is we need to get rid of the real numbers as soon as possible. So we use this trick that I've explained already, this infinite product of 0 to 9, surg x onto closed 0, 1. So we take this ring here. This is power series where you're allowed finitely many t to the n for n negative, and all the coefficients are integers, and you also demand that these power series converge in a small neighborhood of a given real number r, which is related to P. And those power series, that's a very kind of discrete type object. And the idea is that, but on the other hand, if you take a power series that converges at r and you evaluate it at r, you get a real number, and then you get some surjection from this discrete type thing onto the real numbers. And so the next thing you do is you pull back from the real numbers to this funny space of power series. So now V doesn't have to be a real vector space anymore because I've replaced MQ of S by a more discrete thing. And so V now becomes a slightly more general thing, and we keep reducing like this, and at the end of the day, we've got some derived homomorphisms that we want to understand, and this just boils down to some completely explicit statement about some higher X groups all vanishing. So this is the technical result that one has to prove to deduce this big theorem, and if you want a precise statement, then you can just go and look up Theorem 9.1 of Scholze's lecture notes. So it's about some X group vanishing in the category of condensed abelian groups. And the nice thing is because these condensed These condensed abelian groups, these are very nice categories. They have like lots of projective objects and compact projective generators. And so one can explicitly write down a sort of a formula for these X groups by simply resolving the first variable and then doing a sort of a completely concrete calculation. So this is how they attempt to compute these X groups. And one of the key things they use is something called the Breen-Deligne resolution, which is a completely functorial way of resolving an abelian group by some very sort of concrete free abelian groups. And this is a highly non-formal thing. I mean, just sort of resolving an abelian group A by arbitrary sums of things like this is easy, but it's this finiteness issue here that really causes grief. So there's this Breen-Deligne resolution, and unfortunately the proof that this Breen-Deligne resolution exists is extremely delicate and uses a lot of stable homotopy theory. So that sort of unexpected application of sort of topology in what we're doing. But now we know what we've got to do. We've got to check that all these higher X groups are vanishing. And I didn't explain what a Q measure was, but we're now going to get dirty and start writing down some completely explicit abelian groups and checking that various things are exact. And these abelian groups, they all have these sum of norm of an to the power q, and there's various norms involved on these. You want to look at the things whose norm is at most c, where the norm of some measure is going to be some integral of this thing to the qth power. So you unravel this homological algebra, and what happens at the end of the day is that this hard theorem 9.1 just gets reduced to a completely explicit, very, very low-level statement about an infinite family of complexes of abelian groups that have norms on them, or pseudo-normed abelian groups. And you've got to prove that this collection of complexes is exact, but not in the usual sense, in some refined sense where it only has to work for sufficiently large little c, and it only has to work for sufficiently small degree. And by exact, I don't mean exact, I mean a bit more than exact. I mean that if something is in the kernel of D, then it has to be in the image of D, and furthermore, the thing that it's the image of, the norm of that thing must only be like k times bigger than the norm of the original thing that had kernel equal to 0. But what I'm saying, the point I'm trying to make here is that condensed P liquid vector spaces and stuff like that is really, really complicated. But this stuff here, it's all of these definitions are completely elementary. So if you give me like 10 minutes, I can sit and explain whatever your background, as long as you know what an abelian group is and what a group homomorphism is, I can explain precisely what this question is. And it's a question of the form, for all A there exists a B, such that for all C there exists a D, such that for all E there exists an F, such that blah. So it's an incredibly unwieldy, complicated statement, but it's completely low level. And if you want to see the exact statement, then you can look at this theorem 9.4. So the story so far, and this is the end of the mathematics now, the story so far is that Clausen and Scholze think they can revolutionize complex geometry as long as they can prove theorem 9.1, which says that some higher X groups vanish in some fancy category of condensed abelian groups, some sort of quite complicated statement. But if you assume a whole bunch of stuff from stable homotopy theory, they can boil it down to a completely concrete, low-level statement about completely explicit abelian groups, which are mostly sort of subgroups of this group here. So that's the story, and now I'm afraid the rest is waffle. That's the maths, and now here's what happened next. So I got an email from Scholze in December 2020, just asking me if I'd read this document, and I remarked that indeed, 6 months ago we'd had a study group on it at Imperial, and there were study groups on it all over the world, right? And so then he said, right, did you read the proof of theorem 9.4? And I thought it was quite a funny question. But you know how study groups work. We had 2 hours to think about section 9, and theorem 9.4 is this very messy, low-level thing that's got some 9-page proof. There's just a lot of fiddling around with diagram chases. And so the answer was no. We had not read the proof of theorem 9.4. I mean, we'd sort of checked that theorem 9.4 implied theorem 9.1, but we hadn't read the proof of theorem 9.4. And he said, do you know what? No one's read the proof of theorem 9.4. And this is something that Voevodsky pointed out as well before he died. But if you get a Fields Medal, then people just know you're a genius, so there's no need to check the details of your papers, right? Because you're a genius, and so obviously you're not going to make any mistakes. So he says, no one has read this proof of theorem 9.4, and he's not entirely sure that the referee's going to read it either. And basically, he's worried that in 10 years' time, there's going to be some Harvard PhD student emailing him going, yeah, this calculation here on page 53, I can't quite get it to work. You're out by a sign, and the entire theory is going to collapse, right? That's what he's worried about. The proof is 10 pages of messy, explicit, 9.4 is the low-level statement. 10 pages of messy, explicit elementary calculations. And he said, well, what about these theorem provers? Can they do that kind of thing? And I'm thinking, well, yeah, probably. And I'm also thinking, actually, this is kind of a complex theorem about complex objects. So I said, why don't you just challenge, not necessarily the Lean community, but the entire formalization community? Why don't you just challenge them to prove theorem 9.4? Because that would just be an interesting thing to do. And I was writing a blog about my work in this area at the time, and so he wrote a guest post on my blog. And unfortunately, he didn't just ask us to prove the easy thing. He asked us to prove that these X groups didn't vanish. And so that obviously means defining X groups and defining condensed abelian groups. And here's some of the things he said in the blog post. He said basically this theorem is what makes it work. As I say, he'd read it and Clausen had read it. And so as far as he's concerned, he's 99% sure that the argument's right, but 99% sure is, I think he's sort of worried about his reputation crumbling randomly in a decade, basically. And he also says that it was hard to find the proof. The proof is completely low level, but that doesn't mean it's easy, right? It's 9 pages of horrible, chasing around diagrams. So he thinks he's got an argument pinned down on paper, but he now claims publicly in print, I think nobody else has dared to look at the details of this. And indeed, we never found anyone that said, oh, I checked that. So this phenomenon, this Fields Medal phenomenon, I think really does exist. And then he claimed that it was his most important theorem to date. And given that he got a Fields Medal for doing something else, this was really quite a spectacular claim, I think. He really feels like he's hoping to revolutionize differential geometry. Better be sure it's correct. Okay, so we thought we'd go for it. So it was run as an open source project. Everything was sort of publicly available on GitHub. And the first milestone we achieved within about a week and a half, we managed to formalize the statement of this, because we already had abelian groups and group homomorphisms and the concept of a norm and an object. And so it was very, very easy to formalize this incredibly unwieldy statement about being k-exact in degrees at most m for sufficiently large C. So formalize the statement, that's great. So now we've got a level of this game, and the first goal is to prove this, theorem 9.4. And also at the time, one of the other things we did at the beginning was, well, I say we, this is Commelin's doing this. He set up a web page that I can probably find. So there's the web page. I mean, it didn't look like this at the beginning, but there's lots of sort of LaTeX explaining the argument. But also the thing I really like about it was, as well as this, there was a graph. And at the time, so there's sort of the totality of the graph. This is for the easy theorem 9.4. And at the time, none of it was green. Green means you've done it. Right? These are sort of various goals, and you can sort of click on the goal, and you can see the precise lemma written in LaTeX. And the idea is when you formalize the statement of the lemma, it went blue, and when you'd formalize the proof, it went green. So it was kind of, you could sort of see everything was white, and then things slowly went blue, and things slowly went green. And it was sort of quite interesting watching it happening. And let me try and find my slides again. There we go. So that was the blueprint, and everything, because of the nature of it, it was very much sort of modularized. Somebody could come along that you'd never heard of, and they could just say, "Oh, I proved one of your lemmas," and something went from blue to green, and you didn't need to check the proof because the computer had checked it, and they didn't need to understand why we needed to prove this theorem because that wasn't their business. They were just sort of filling in a gap, and so the number of gaps would just sort of slowly get. At the beginning, there were lots and lots of things needed doing, and then sometimes more things would appear. Sometimes we would have one goal, which would be like one sorry, and then somebody would rewrite, somebody would start to prove this one sorry. Sorry just means I've skipped the proof. We'd have one sorry, and somebody would start on the proof, and then they would skip lots of other things, and then there'd be 10 sorries. So the number of sorries could definitely go up as well as down. It started as 1, and then it sort of got to 100 at some point, and then it went back down again. So it took just under 6 months to formalize the easy thing, the thing that Scholze was concerned about. And then, of course, now we've got the job of deducing this statement about X groups from this completely basic statement about infinitely many families of complexes of abelian groups with norms on. And Scholze was always on hand. He seemed to be genuinely interested in the phenomenon, and he was always on hand. He would hang out on the lean chat, and we'd ask him questions, and he would answer very quickly. And he was very, very pleased when we formalized 9.4, because although we hadn't done it, like the challenge is to formalize 9.1, but when we'd formalized 9.4, he knew that he was in good shape, because that was the part of the argument that he felt was that was where the mistake was going to be, if there was going to be a mistake. And so he wrote a second blog post, getting super, super excited that he finds it insane that interactive proof assistants can now actually do this kind of thing. And he also said, I don't know, this is sort of a summary of what the problem was. The assistant was an assistant in navigating through the thick jungle that this proof is, and he says explicitly, the key problem I had, I was unable to keep all the objects in my RAM. And it's not because it was complicated, it was just like super, super unwieldy. This was the thing. You were trying to prove some really, you've got to prove it by induction, but like the actual statement you've got to be super precise about what you're trying to prove by induction, and then the inductive hypothesis, you've got to make sure that you don't ever cheat. So this is what he felt that the theorem prover had given him. It was maybe less smart than him, but it had more RAM. So that's what he had, and then things just really blew up. And this is not what I was expecting at all. Next thing I knew, Nature was wanting to interview me, and there was like some big article about this stuff there. So you don't often see pure maths in Nature, and there it is. So I was very pleased about that, because it's good, just promoting mathematics in general. So that was nice, but unfortunately we hadn't finished the challenge, and I've nearly finished the talk. We hadn't finished the challenge, which was to prove that some category, some higher extension groups in some category of condensed abelian groups vanish. And the problem was that we didn't need anything about condensed abelian groups to do 9.4, right? That was just an undergraduate level statement. So now we've got to start developing the theory of condensed abelian groups and the theory of homological algebra and derived functors and X groups and blah, blah, blah. And then there was also this problem that we had to develop a huge amount of stable homotopy theory to resolve an arbitrary abelian group by these things in this functorial way. That should say ... It goes on there. But this is a bit like, it's quite difficult to even work out what the next term is. It's a very strange thing. This is the map that sends an A to A, and that has a kernel. That has a kernel containing things like box A plus box B minus box A plus B. And then you fix that by sending A comma B to that element, and then this 2 is the statement that abelian groups are commutative, and this 3 is the statement that abelian groups are associative, and then the next thing here is some kind of pentagon axiom and hexagon axiom. It's sort of quite a terrifying thing. So we spent a lot of time ignoring that problem because it didn't look easy, and we didn't have any homotopy theory, let alone stable homotopy theory at that time. And so whenever we needed something that came from that resolution, we'd just skip the proof. And then Commelin started asking whether actually we needed this theorem at all, this Breen-Deligne resolution. because he was just playing around with general resolutions, and he'd found another, it's not quite a resolution, it's not exact, but it was a complex, something that we started calling the Commelin complex, which was very easy to define, completely explicit, wasn't a resolution, but somehow the error was sufficiently bounded that the application would still work. That was the key insight. So that was cool. This is new mathematics happening, which was not what we expected. And so finally to 9.4. So the proof on in the PDF document that 9.4 implied 9.1 was 5 lines long. We did 8 pages, and it took us 6 months. And now we've got these last 5 lines, and they took a year. Because they just said, just apply the theory of derived functors, which just wasn't there. So we had to make a bunch of stuff first. So the reason it took a year was not because it took a year, it wasn't because there was a year's worth of ideas in those 5 lines. It was just simply because the 5 lines were talking about constructions that we didn't have yet. So we had to build a huge homological algebra library, but the point is, it's there now, it's built, and it's in Lean's maths library, so we don't ever have to build it again. So that's kind of nice. And so that's the end of the talk, really. Now I just go sort of 1 or 2 slides on what just happened and what did we learn. For me, the main thing I learned was that this was the big open question. Because you never know, is the theorem prover just going to grind to a halt, spend 15 minutes trying to check your theorem and then run out of memory? It wasn't clear at the time that this software could actually handle this kind of question. So we learned that this kind of project was possible. I mean, we also learned that it was possible to collaborate in this very weird and exciting way. Commelin needed some results about truncations of complexes, so we just wrote down the statements he needed. He didn't prove them, and then a few days later, I noticed that these statements had appeared, and I had some time, so I proved them. And I didn't need to know why he needed them. It was just, you just fill them in. So that was really nice. And then, and then the other thrill is that you see these boxes. Everyone gets very excited when another oval is about to go green. And we learned that the proof was correct, which was good. And in fact, it wasn't correct. It was, because of course no proof is really correct, right? Somehow anything that's 8 pages long is going to have some slip somewhere. There were several little slips. And there was one slightly bigger slip. In fact, the first slip I found was the very first day I started on this project. I wanted to prove some technical induction statement. And the inductive step was fine, but the base case was wrong. And the base case being wrong is really common in mathematics, much more common than you think. Check the base case. The base case was wrong because, and so the entire proof had to be rewritten, 50% of the J's had to become J plus 1s. And that was that's not my problem, that's Peter's problem. But you told Peter, and the day later it had all been fixed. And we did find one problem, that actually there was a certain inf that wasn't attained, wasn't obviously attained. And so an epsilon had to be added, and then a whole bunch of epsilon suddenly appeared, and then you were just oh, blimey, I hope that I wasn't relying on x less than or equal to x, and it's now going to be x plus epsilon less than or equal to x, because then I'm going to be dead. So he was, apparently Scholze was a bit worried for a day or two. Under a day. He'd fixed it the day later. So the proof wasn't quite complete, but it's complete now. And as he said afterwards, this is exactly the sort of thing he was worried about. So yeah, the proof walks a fine line, as he said. And he also argued that the process gave him more insight into the proof, which I thought was a very interesting thing to say. The key thing was a reduction from a non-convex problem over the reals to a convex problem over the integers. And there's a corresponding math overflow post about this. So there's some weird things, and that's the end of this slightly weird story. Thank you very much.
We should have time for some questions. Anybody? Yes.
So you had said that somehow in the original proof, the stable homotopy theory is where the topology comes in. And it seems that you'd expect some topology to come in somewhere, just because it is actually, at the end, replacing all the topology in the previous theory. Mm-hmm. But if you get rid of the stable homotopy theory, where is the topology hiding?
It's just in the norms. I think,
Okay,
I think
so-
it's still there, but it's in the norms. So it's a particularly nice kind of topology.
No problem. Anybody else? Okay, then if not, then let's thank Kevin again, and we'll hope to see you all next year for the next Bernays lecture.
Thank you very much.